तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We are looking into the design of RAM, and we have seen how to design a dual RAM, and which was on chip, that is internal to the chip we are designing, be it FPGA or ASIC. And we will now consider how to interface with external RAMs, and this is important to locate the RAM externally in some of the applications. For example, for video scaling, you require huge memory storage. For example, for the picture size of 1900 by 1600, 1600 by 1200 pixels size, color motion picture would require per frame about 2 MB for one color, and for 3 colors 3 times that, say 6 MB, and that will be the size of the RAM that will be requiring if you are to store just one frame. And if you require 2 frame storage, double that capacity will be required. So needless to say, we need for such applications RAMs which are external to the FPGA or even ASIC. And so what we have here is a design for such a controller which will connect to the external RAM. And looking at this figure here, we need these controls in order to interface with the external RAM onto the FPGA that we will be designing. And this design will be housed in the FPGA or ASIC which we design. And clock out is the system clock for the memory, being a synchronous system, and there will be a reset as usual, and there can be a hold, and in order to hold the process. And in addition to this, we need enable for the external RAM, and this what is shown here is only controller for one RAM, and in cases like video scaling or data compression, we need dual redundant RAM. So in which case we need to select this give an enabled signal as well for that. In addition to this, we need 2 sets like this for the 2 RAMs, and these signals are CE stands for the chip enabled. If you have 2 RAMs, naturally CE1, CE2 you can have. Similarly, this is a write signal for the external RAM, and this is the read signal for the external RAM. OE is output enabled. Normally the nomenclature used in most of the memory vendors is precisely this. And as usual, we have one read, that is a change here. We will make read low, read active high and write active low. So RWN is the one which will select between two RAMs in case we have that. In addition to that, it also serves the purpose of telling us whether we are writing into the RAM or reading, and we can use in the test bench appropriately here. And there is also an address bus for 16 bits, that means it can address an external RAM of 64 kilobytes. For higher memory requirements, you need to jack up this here. So, this is the design for the video scalar external memory RAM controller, as I mentioned before, and this is the maximum number of address location that you will encounter in a 64K, this is in decimal here. And we first declare the module for the external memory. This is the controller design we are looking into, and all the IOs that we have seen on the diagram is listed here, followed by the declaration of IOs all here. This 15 through 0 is for address, and all other signals are here. And in addition to that, we will be requiring we have assign statements using this some of these outputs, and therefore they need to be declared as either wire or reg. Here it is in as a register, because it falls as in always block with positive edge of the clock. In addition to this, we need read address and write address separately for the video scaler. Therefore, it has been bifurcated in this fashion, and again once again the width is same as the address what we have considered, and this is next value, whereas these are all the registered values. And similarly, there will be one for address write, there will be one enabled signal internal used, and also since we are using external RAM, we will not be in a position to achieve that high speed that we can with the on chip RAM. And for example, you may have to scale it down by a factor of 2. For instance, if you are operating the system clock at 100 megahertz, we can access external memory only at 50 megahertz rate. So, in order to do this one, we have a counter here. The counters are separate for read as well as write. So, in order to enable that counter, we need another signal, and they are all assigned statements, and that is what and in addition to this, for write address we have a read address, and similarly write count next also is required in the course of before registering, and we also have some resetting the address and resetting write address similarly for other signals, such as write counter is register, and enable read counter, and its next value, and read count itself here, and this is enabled, this is the actual counter, and it is only a single bit counter, it just counts 0 and 1, it is merely a toggling flip flop. And we have further read address reset as well. Now we will have a look into the actual Boolean expressions that we need to evaluate for achieving this, and first is the reset address. So, whenever you want to reset the actual address, so what we have to look for is whether we have already processed the maximum all the addresses right up to the maximum. This is the 65535 in this case, and when it matches with the current running address, and then if the write counter or read counter is 1, as I said before, the write counter is to scale down the speed of the access memory access by 2. That is the reason why we have 1 bit counter for separate counters for write as well as read, and whether this counter is 1 or this counter is 1, and it will go from 0 to 1, it starts with a 0. So, we take every alternate clock only we need to process, and together with this we also need a chip enabled, and when it is enabled only then we reset the address. So, the address resetting means when it touches the running address will be from 0, 1, 2 etc. 65, 535. When it touches 65, 535, then you this signal is created, and we have one register here for creating this RWN, which we have seen earlier, and this is meant for whether selection of read or write. for example, if it is 1 it will be a read, otherwise it will be write. And as usual we have taken for reset hold condition and what we should do. So, this is initialized to 0 here at the power on reset, and when reset address is encountered, what we need to do is just change this RWN, invert it, that is what we had to do, because we can access the next external RAM in the case that we have dual RAM. So, we need an enable for write counter, and that is derived from the enable RAM being high and then RWN being low, that corresponds to write here, that is why we have a write counter here, and also CE must be activated, that is chip enable must be active. And in this always block, note that we are creating at negative edge. All along we have seen at positive edge clock, we also use the negative edge clock here in order to create address at the positive edge of the clock, and following negative edge this write pulse is issued, so that when a write pulse is issued, the address is always stable. That is the reason why we have designed in this fashion, and that is the reason why we need a negative edge of the clock here, and this creates the write signal for RAM. And once again these are all the usual reset and hold, and so long as it is enabled as we have seen before. So, what we need to do is invert the write. If it is in the write pulse is not there, if that is active high, I mean it is not active high, it is in high position. So, we need to clock it, I mean make it low. So, that is possible by inverting here, and if it is already low with the arrival of the next clock pulse at the negative edge, this will go high again. Thereby you create at every 2 clock cycles one write pulse which is active low. Otherwise you just take it to the safe state of 1 being active low here, and then what we need to do is increment the counter, and this is advanced increment, and in this always block at positive edge again here. So, what we do is we reset the counter to start with, and when write count is 1, that is counter is running between 0 and 1. So, whenever it is 1, that is the identification of the second clock, only then write count will be forced to 0. That is the reason why it is going from 0 to 1, and so long as that enable is activated, it will keep counting. That means to say it counts from 0 and 1, and similarly we will have a read counter, it is exact counterpart. So, I do not have to explain at length that one, and before that we have write address generator here, and this is advanced increment here, and we increment only with this enabled signal here, and that is enabled only if that enabled RAM is activated, and read write is in write mode. So, WN here, and also write count is 1, that is the second clock only we process. Further you need chip enable active here, and there is also a reset write address, and which again is dependent upon the maximum value of the address that is encountered for write address, and once again that write counter 1 and C is also taken into account here. And in the next block we process the actual that is only an assign statement earlier. So, what we do is we really process only here based upon the reset write address, and we have seen there, and we reset the address because it has touched 65535. So, we need to reset that one, and it will be reset at this point of time, and so long as the enable is on, which we have seen the condition earlier, and the write address is incremented, this also we have seen in an assign statement earlier. Similarly, we handle the read counter as we had done before for the write counter, and it is precisely the same except that read is replaced, write is replaced by read, and this is advanced increment, and actual read counter is processed here, and so long as read counter is 1, only then it is made 1 0. So that is 0 is made 1, 1 is made 0, and so on. It keeps on toggling by these two expressions here. Is exactly the same as write counter. And once again assign statements are there for read address, and it is exactly the same as write address we have seen before, and exactly matching condition except for the fact that read is 1, that is in read mode, and earlier it was 0 for the write address. And in this block we actually take that assign statements results, intermediate results, and then process accordingly. For example, when the terminal count is reached, it is reset here, and otherwise it is incremented here. Advanced increment was shown earlier, and if none of these conditions are satisfied, we simply write it back to the same thing, that is not disturb the contents. So we have a enabled read counter, and that is based on enabled RAM being high, and read write is in read mode and chip is enabled. For this condition, what it does is read signal for RAM, that is this is the read signal we generate for the external RAM access, and if it is reset, this is active low, therefore it is taken to a safe state here, and for hold it is preserved, whereas for enabled read count we invert that OE. This is on similar lines as the write, it is precisely similar meaning here, and otherwise we take the read to the inactive state. By this means we can have a true random access, in the sense that we can change address and change from read to write, and vice versa. Then at this step here, what we need is a single address to go to the actual RAM, and that address may be either a read address or write address, and that depends upon the read WN control. If it is 1, it would mean read, that is here, and if it is 0, it would mean write here. So when it is 0, it is write, therefore this condition being satisfied, it will return 1. For 1, this is the condition, this is the mux that you are already familiar with. So your address gets either write address or read address depending upon RWN, and you have also a CE generated here, although this is a rather a dummy statement here in this example, because we use only one single RAM. In dual case RAM, we can give a meaningful address and then select one of the two RAMs, and this is also a mux statement, and that is the end of the module here, and this completes the design for the external memory, and we will look into the test bench for the external memory. So as usual, we want 100 megahertz clock, so we initiate this value to 5, and maximum address we want is 65535, and this is the last location of the external RAM, and what we want to do is, first we want to write a known data pattern. For example, all 5 means this RAM is 24 bit in width. So this is because we need it for video scaling, and we need to process 3 colors for the motion picture. So that would demand 3 bytes, that means 2 for red, and another 2 for green, another 2 for blue. And if you want to test for some other data pattern, you are free to do so by merely changing this. For example, you can change it to all A's or all zeros, all FFs. I suggest that you take in turn and check this. Then we need to include the design, which is external memory, and we had to call the module. This present module is the test module, that is the external memory underscore test, and what we need is address, then chip enabled write and read pulse, and address is 15 bits in width, and all other bits are single bits, all other signals are single bits, and we need to declare clock out as reg, because this is an input here, and all the outputs are declared as wire here, being a test bench. Inputs must be reg, that is what we have here. In addition to this, we also have one data, and this is the test data that we have input in the test bench, and in this case it was all 5s, and this is the special instruction that you are already familiar. What we are doing in this test bench is we are having an external RAM simulated right in this test bench. We do not have an external RAM. So, what we do, we create an external RAM right within the test bench by using this reg mem, which is a special instruction for invoking arrays using flip flops, and you can have this is the maximum address that you can have in decimal. So, for example, in this case it is 65,535, and the width of this memory is 24 bits, as we have already explained there. That is what is mentioned here. Simulate external RAM 64K into 24 bits. Because we need 3 colors, we need 3 bytes or 24 bits, and we instantiate the external memory design with all its IOs here, and we use ports by name, and once again we start the initializing here of clock out, reset, hold, enable RAM to the respective save states. For example, reset is inactive state here, and we apply the reset pulse only at this point of time at 10 nanosecond, and withdraw the reset at 30 nanoseconds. Just for 20 nanoseconds we apply a reset pulse here, so that the controller resets whatever internal registers that are being used here, and so this will, I mean, the actual design has automatic change of address. So, you do not have to, in the test bench you do not have to, there is no need for you to change the address, and it is all automatic covered in the actual design, which we have seen before. And what all we have to do is just terminate the whole process after a delay, and note that a huge delay is so many clock pulses are required for the delay, because we are treating 64,000 locations, and each we have seen takes 2 clock cycles for either a read or write, and we have read as well as write as well as read to be performed. That means 2 plus 2 into 2 and 64,000. That means if you multiply, you will get this figure with 1 cipher less. The extra cipher is arising because each clock cycle is 20 nanoseconds. So, you multiply that result by 20, that is 2 into 2 into 20 into 64K must come close to this. That is the reason why we have such a big value here, and after this value the test bench will automatically stop the testing. Although we have written elaborate test bench like this in order to write a particular data pattern, say namely all 5s for all the 64,000 at one time, and then in the next phase we will change over to the read mode and check that all 5 5s are intact, and that is what the test is, and the result of this test we should be in a position to indicate as a go no go test. I mean, that is to say that whether the test has passed or failed, only that must be reported, and no unnecessary locations reported or address reported. And before we wind up the test bench, so what we have here is one always block which takes this following action here, and for RWN or address changing, and this one notice that it is a read or write mode selection, and here if it is 0, that is if it is write, what should happen? You should write the test data. This data was initialized to all 5s here, and that 5s will have to go into the memory, and this reg mem we have seen to be within the test bench, and to start with address will be 0, and that is what we have seen while looking into the address, and initialize to 0 at the power on reset. So, it starts with a 0 and automatically the design increments the address, and also applies a read or write pulse only every once in 2 clock cycles. So, automatically the design takes care of writing into this RAM, although this external RAM is within the test bench here, and to this particular location addressed by the controller will be written into the data test pattern, namely 555 will be written into the ROM here in the test bench. Write data first into the external RAM all locations. So, what we do is we write all 555s in every location. There are 65 535 locations, all locations it will write the same data in the first phase and then change this RWN and then start reading in order to check whether the contents are still 555 and that is what we do here. And in order to do this one we look for the change of address, and earlier always block is also a combinational as much as this block, and read data from the external RAM and check with the return data for all locations. That is what we have said here, and we use a case in order to do the read operation. So, read operation we do, just note that this is a concatenation here, it is actually 3 bits only, all this put together are only 3 bits as is depicted here, and this first one refers to the returned value of RWN equal to 1. That is to say, if RWN is 1, then this whole bracket will return just 1. If it is not 1, that is if it is 0, it will return 0. So, this particular bit pattern is test for the complete bracket, I mean whatever is mentioned within brackets. So, also for the entire thing here. In this case what it says is check the read the memory whose address is given in ADDR, that is from the external RAM which is in the test bench, and compare that one with the test data that we have already written. I mean it is initialized in the test bench, that is all 5s here. If it is equal to 5, the red content, then only it will, this whole thing will return 1, that corresponds to the second bit here. And third case is when address is the last address, for example address is the current address which is running in the design, and finally it will be incremented right from 0, then 1, 2, 3 and so on, it will go right up to 65535, and when it touches that value, that is what is here, and this equality will be satisfied, then a logical 1 will be returned, and that is this here. And in this case what here means is we are in read mode, that is what we want, and memory address is also verified, I mean with the data already stored, and that is why 1 is returned here, and here this is the very last location that we have read, for example 65535 location. That means to say we have earlier we have already read all the 65,000 locations, and we are right at the fag end of that RAM test, and when this happens what should we do is we further have one more flag, this is also a signal calling error, and during the course of writing and checking back every location, it may so happen that one of the locations is faulty, in which case an error flag is set. This will be seen later on, and if that error is 0, this is it would assure us that there were no errors reading from any of the locations including this last location, that is 65535 here. So, when there is no error, and what we should do is just display this external RAM test pass. As I mentioned, after checking all the locations, it will simply report that external RAM test is passed, and if error is encountered on the other hand, we had to report it is failure. So, we will report failure, and after reporting this one, we should not forget error flag to be set reset, because in this case error flag would have been set, that is made 1. So, you should not forget this here, that is why a begin end is given, because more than 2 instructions are used, statements are used. And next combination in the case can be 101. So, in this case 0 corresponds to then error here, and 1 corresponds to the very last memory being processed. So, that means error has been encountered, and this error has naturally come only for the very last location 65535. Therefore, we report this external RAM test fail, and we also report the last address, namely at it, it's like a C comment here, I mean C statement, precisely a C statement, and that is why we use only in the test bench. We should not use such statements in the actual design, and it is precisely the same syntax of C. Address is the variable which is the running address value, and that is in decimal, and this whatever is the actual address will be output here at 65535 it would have reported if there is an error at the last location. And another thing is last combination here is 100, which implies we are not in the last location. It may be any other address other than the last, right from 0, 1, 2, 3 right up to the last but 1, and when there is an error for any of the location, this error flag is set. That is what I mentioned earlier, error flag is set later on, and it is here the error flag is set here, and the error can occur at any location and it will be promptly recorded by this statement. And we have covered all the conditions except for I think 110001 11 condition we have covered, that leaves 10. So 110 we have not seen. So should we see for that, that will be covered under default. If error is encountered in any location except the last, that is what is the statement for comment for that, and if there is a default, take care of other possibilities. Other possibilities are 110. So 110 means there is no error, but this is not the last location. So we do not have to do any work there. Therefore, a dummy statement is written for as a default, and for other combinations it will be only 0 here. So 4 combinations will arise for 0, but 0 corresponds to read, write. Therefore, we do not have to take any action. So all those 5 states are automatically covered in the default, and we started with a case. Therefore, there is an end case, and what this instruction statement does is we read memory particular address location memory and assign it to data, so that we can view this also when we view the waveform. And this is an usual statement we have been using for running the clock by inverting the clock, and this is the end module for the test bench. So before we see the synthesis results, we will have a look at the waveforms. The first thing what we had was, this is the model sim result. You can see that external RAM test is passed. So it is a go no go test. This is how it reports here. Had there been any error, it would have mentioned fail and corresponding location or something, it would have reported. And you can just zoom here. So this has been we have taken back an iterator file, and that is why loading shows all the primitives there. And finally, we have run the actual process, and it had run that external memory back an iterator file and reported it, the test is a pass. That means all the 65,535 locations have been successfully written into and read back. This is with only data 555. You can experiment with other datas, and going to the waveforms. So here I will first read out before zooming. We have a clock out here, and this is the clock signal operating at 100 megahertz, and this is the address that we have. It may be a write address or read address here, depending upon this RWN control. So if it is 0, it means write, and it is right now in the write mode. Because the start we want to write some data, and let us see what data we want we have. We have same all 5 files. You can see 2, 4, 6 files are there, and the same data is being rewritten. That is the reason why it is changing here at every write point, and address counter is also changing here, 0 here and then 1 here and so on, and it keeps going. And the actual RAM is enabled only at this point of time. Therefore, it starts functioning only from this point of time. In fact, from subsequent positive edge only it is actively processing. And at every note that this counter is address is changing only for once in 2 clock cycles. The next clock cycle it does not change, and this is the reason why okay, we will have a look at the write pulse here. So, for example, you need to select the chip, so we make the chips low, and the test bench we had made it here, and RW1 is in write mode, as we have seen it is low, and chip is enabled all through, and write pulse is applied for this is corresponding to the 0 address here, and write pulse is applied after the positive edge of the clock here, and so that address is always applied at the positive edge, you can see here, and always at the positive edge address is changed, whereas the write pulse is applied only after the address stabilizes. So, we give and register at the negative edge here. So, that is what we have seen in the design, and this is created at the negative edge, and because it is back annotated, there is a delay, you can see. And here we have a write counter running, and this toggles because it is only a single bit 0 1, and this is what is responsible for making this write pulse or read pulse when we see, and read counter will be activated later on. So, now if you see here, what we have seen is just a few samples here, some up to 5 location, and we will see other waveforms to, okay, before this we will just zoom so that you get a grasp. So, clock out, etc., address changing here, this is the clock, and this is the data, it is changing here, and write counter, read counter, write counter is this, and OE is this here, that is what we have seen. So, we will look at another waveform. So, this is the fag end of the test. So, it is 65532 and then 65535, then it rolls over to 0 here, 1 2 3 and so on. This is the address here, and now let us watch what is happening to this RWN control. It is all along low, that is what we started with. We started writing for every location up to 65535 the data, that is 555, which is at the bottom, and now you can see that write pulse has stopped here because write is over with 65535, and soon after that this address changes to 0, and also that RWN control changes to 1 here, so that we can start reading, or I mean this being 1, it is a read only mode. So, now also notice that this OE bar is the read signal here, OE bar has started become active here, and write has stopped. So, the safe state is high state, that is inactive state for the write, it is both are being active low, it is a designed active low, and that is why it is like that. And you can clearly see that write pulse stops here, and with the switchover of RWN, and reads starts here, and once again you can see that write counter has been running in support of this write counter. Now it has, this also is stopped here, and instead read counter is activated here, which aids in the generating the OE bar signal here, and the data is now there is no change of data because it is continuously reading the same data, and you can see huge time has elapsed, and for 65 535 locations we have not only written 555 data, but also cross checked, and you can verify whether there is an error. You can see here, this is the error here, and it is 0, this is lower than 0. So, there has been no error, and we have seen in the model sim window that it reports the test is passed. So, coupled with this should prove that the whole thing is working, and the zoomed version is here. So, you can see the clock out and address here, and switching over to 65535 and you can see that RWN changing to read here, it was write here, and that is RW1, then chip enable is always low, it is at the bottom of this. So, if it is high, it would be on the top of this. So, you can see here it is on the top. Write signals are activated here, and OE is deactivated because there should be no read pulse, and write counter is activated and there is no read counter there, and that is what you see all through. And finally, you have seen error being 0 here, all through it is 0, and this is what we have applied data, and it was changing because write pulse was active, and it's there is no change during read phase. So, we have one more waveform towards the end. So, that is when it is complete. So, the next address will switch over. For example, it was earlier it was high, and this is the second block as such, and when it touches the highest value here, and RW is again made low, meaning thereby it is taken to right here, and with this we have done not only a write but also followed by a read. So, this completes the test, and beyond that it is a dummy running here. We are not really interested beyond this, because with this it has already reported error to be 0, and in model sim window we have seen that it has reported correctly. And so we will go back to the synthesis results and for this external memory, and mind you, the design does not contain the actual memory, it is only a controller. So, you will see that gate count etc. will be less, and the operating frequency reported by synthesis is 96 megahertz with the same device that we have used before, and it has taken only 69 LUTs, and Xilinx place route results are here for the same thing, and it takes some 1800 gates only, and speed probably has improved to 119 megahertz here. So, we are justified in running at 100 megahertz, that is the clock rate is 100 megahertz, whereas the access is 50 megahertz. So, with 50 megahertz we can have actual RAM. It has been this has been designed with vendor's device as such taken into account. So, that means to say that is a standard RAM available, so that we may use later on in the actual project, that is 64K into 24 bits. And before we wind up, we have some assignments for you. I will quickly read, and you will have to solve these problems. So, first we had this covers the entire memories, and we will look into the assignments for ROM. ROM can be tested by finding out the checksum or signature for the specified address range. The signature can be either 1 byte or 2 bytes in width. It is obtained by adding the succeeding locations bytes at a time, ignoring the carry every time. In this manner, all the bytes are added up, that is accumulated, to get a single byte checksum. In the case of double byte checksum, addition is carried out on a word by word basis, ignoring the carry generated at every addition. A word consists of 2 bytes with lower order address as the MSB. The final checksum in this case will naturally be a double byte. The checksum expressed in hexadecimal provides a very convenient go no go test. This also serves the purpose of identifying the program or data stored in a ROM. Write Verilog code to implement the computation of the single byte as well as the double byte signatures for the ROMs we have designed earlier. The address range must be user specified. So, the user will you have to write a test bench in order to compute the checksum. It may be a single byte or double byte, which will take an example and explain, and you have to write a test bench for that, and I should assume that user supplies the actual address range. For example, this is the address range user will supply, and you will have to take input this information and then compute on this checksum what we are going to explain now, and then report finally whether it is a pass or not, otherwise not pass or fail, but the actual signature. For example, if it is a single byte signature checksum, what we do is we add these 2 bytes and ignore the carry from this. So, keep the result and add repetitively the subsequent bytes. For example, that result you add with this one, once again ignore the carry and keep repeating till you have exhausted all the data, and finally you will get 1 byte answer, and expressed in hexadecimal is the checksum. It is also known as the signature, and you can also have a double byte signature. In this example, single byte signature, if you compute manually, you will see that it is FC in hexadecimal, and if it is double byte checksum, it is FF FE. And how to get this double byte signature is you put this second byte here and treat the whole thing as a 16 bit number. Similarly, put this one here and treat it as second number. So, you had 2 16 bit numbers, add the 2 as if it is a whole 16 bit each, and ignore the carry as we had done in the byte checksum, and result will be again 16 bits, and repeat the same thing for this group and this group. Finally, you will get a 16 bit checksum, and that is also known as a signature. For this example, it is FFE. So, we have an assignment for RAMs. There are 2 assignments. I will read it once again. RAMs can also be tested in the following ways. First is what is called RAM test. Normally, these tests are very popular in microprocessor based design, and the RAM test and walk test it is called, and in this test is conducted at one location. Earlier we have conducted at range of locations, whereas this is conducted only at a particular location, and this holds good only for RAM, where it can read as well as write as well as read. To start with, zeros are written into all the data bits in a byte and read back to make sure that the read data is intact. So, what you have written into, you should make sure by reading, and that same data is still intact. The data is incremented by 1. If it is 0, we increment it to 1, then 2, and so on, right up to 255 if it is single byte. If it is high precision, say 32 bit data, you will have to go right up to the corresponding decimal value. So, this needless to say, this will be a very time consuming test, and and the above process is repeated until the maximum possible data 255 decimal for a byte based test is encountered. The user specifies the address location for which the RAM test is conducted. Write and test the Verilog code to accomplish this test. So, write accordingly. So, there is also a walk test. This test is conducted at 1 byte location as in RAM test. The user specifies the address location as well as 1 byte data to start the test. Write the user specified data into the address location of the RAM under test, and check the RAM back to ensure that the written data is correctly read back. At the second step, rotate the data in the RAM right by 1 bit and check the written data is correct. Continue this test till all the data bits are covered. Write the test bench in Verilog and test the same for the RAMs we have designed earlier. Assuming the specified data is 4 ones followed by 4 zeros at RAM location 1000 H, for example, the test has to walk through the following data pattern. We are testing at this an illustration with an example. So, what we need to do is user will have to specify what data to be written at what location. This location address as well as data will be furnished by the user, and you have to take that as an input for this test and conduct this test and then report whether it is a pass or fail. And what we do here is, suppose the user has given this as the data, what we do is we write this data into this location, RAM location, and check back to make sure that it is the same data. And then at the next step, what you do is rotate this one. You may have some sort of accumulator wherein you rotate and then write back the rotated value here. Rotate in sense, this 0 will rotate back to this position. So, every time you rotate by 1 and then write it as well as check the data written is correct, and keep repeating every time shifting by 1 or rather rotating by 1. So, when you come to the last one, when you rotate this one will go to 1, which will be the same pattern as we started before. Therefore, we do not test that condition again. So, you just exhaust all possibilities here, being an 8 bit. So, you need only 8 such types of write. After this writing, when all are successfully written and checked back, you report pass, and this ends the memory design, and thank you.